So we have seen the final cout expression from the XOR gate, and that you can, for generalized term, you can call it as Cn. That is, carry out will be equal to Gn plus Pn into Cn minus 1. So where Gn is A multiplied by B, that is A into B. This is the carry out of half adder first, and Pn is A XOR B. This is a sum of half adder first, right? And so this Pn has to be 1 so that carry can propagate. Which carry can propagate? Let me draw that half adder again. So this is first half adder, and this is our second half adder. So here two input will be there, A and B. So two output will be there. First output carry will be there, right? That this we are calling it as the Gn. For generalized term, you can call it as An and Bn. So here you can write An and Bn, right? And here it will be An XOR with Bn. And this we are calling it as a carry propagate. Why we are calling it as a carry propagate? Because this has to be 1 so that our carry in minus 1 to propagate to the output. So this is flowing to the one input, and this is again flowing here. And carry out of this second half adder will be Pn multiplied by Cn minus 1, and sum of the second half adder will be Pn XOR with Cn minus 1. So Pn is what? A XOR B XOR Cn minus 1. So this is our sum, final sum. And so this has to, so if both of these conditions are true, then our carry will be generated. If either one of is also true, then also our carry will be generated. So this is our Cout, or you can also call it as Cn, right? So Cn will be equal to what? Cn will be equal to this expression. This circuit is clear?
Yes, sir.
Yes, sir. Yes, sir.
So Cn, let me finally write down. Cn will be equal to Gn plus Pn into Cn minus 1. So one by one we will put, this is generalized expression. So if n is equal to 1, for n is equal to 1, so this will be C1 G1 plus P1 into C0 for first stage. For n is equal to 2, it will be C2 will be equal to G2 plus P2 into C1. Now value of C1 you have to put it from here to here. Substitute the value, so this will be G2 plus P2 into G1 plus P1 into C0. So this will be equal to G2 plus P2 G1 plus P2 P1 into C0. Just pay attention that this C2 is now not dependent on C1, which was earlier in parallel adder case. Well, while we are doing 4-bit parallel adder, whereas if you see here, C2 is only dependent on C0, which is the carry input from previous stage, and all of these, that is G2 and P2, are nothing but G is what? AB, and P is what? A XOR B for that particular state, right? So now we will put n is equal to 3. So it will be C3 will be equal to G3 plus P3 into C2. So value of C2 we will put it from here to here. So this will be G3 plus P3, and C2 is what? G2 plus P2 G1 plus P2 P1 into C0. Simplify this. So this will be G3 plus P3 into G2 plus P3 into P2 into G1 plus P3 into P2 into P1 into C0. This is our C3. Similarly for 4-bit, because we are doing for 4-bit adder, so this is n is equal to 4. So this will be C4 will be equal to G4 plus P4 into C3. The value of C3 you have to put it from here to here. So this will be G4 plus P4. C3 is what? G3 P3 G2 plus P3 P2 G1 plus P3 P2 P1 and C0. Now simplify this. So this will be equal to G4 plus P3 into G3 plus P4 into P3 into G2 plus P4 into P3 into P2 into G1 plus P4, P3, P2, P1 into C0. This is our final C4. That is a carry out, or you can also call it as carry out. So you can see this carry out, final carry out is not dependent upon the previous carry, but only dependent on the input carry. This C out is only dependent on the input carry. Right, so it does not have to wait. Obviously, some processing time has to be there to implement this G4, this logic, right? And if you see this logic is currently in SOP form, that is sum of product form. So this you can implement it using NAND gate, that is universal gate. And how to implement it? You can double bar this, right? So you know how you can implement it. Now you can now you can reduce this expression. So this will be equal to G4 bar multiplied by P3 G3 bar multiplied by P4 P3 G2 bar multiplied by P4 P3 P2 G1 bar multiplied by P4 P3 P2 P1 C0 bar and whole bar. So this logic you can implement it by NAND gate. That is, let us say this is C4. How you can implement it by NAND gate? So in the first input G4 is coming, G4 bar, and this then P3 G3. So this is flowing through the NAND gate. The output will be P3 into G3 bar. Similarly, you can implement rest of the logic, and then one more NAND gate is required to where all the input will flow, all the input will flow, and finally you will be getting this expression. So in this way, you can see that where earlier in 4-bit parallel ladder, more propagation is delay is there, whereas if you compare with this, so here only 2 levels of delay will be required. So 2 levels of processing will be required, one from this level and one from this level. So hence the processing time can be delayed. If you go for 8-bit or 16-bit or 32-bit or 64-bit, then a large time can be saved if you implement this carry look ahead adder. This is clear what I'm trying to explain?
Sir, can you explain again?
Which part?
Sir, from that SOP part.
SOP part. Okay. So here you can see that our carry out, final carry out is not dependent upon the previous carries, but it is only dependent upon input carry, right? So if given, if any number is given, suppose 4-bit number is there 1101 1011. If this number is given and it has been asked to add this number, so how you have added this number in previous cases, you have added 4 parallel adder, right? 4 parallel adder. Let us say this is full adder 1, full adder 2, full adder 3, and full adder 4. And here C in was there, input right now it is 0, and here A and B terms will be there. This can be A0, A1, A2, A3, and this can be B0, B1, B2, and B3. So now this will be A0, B0, A1, B1, A2, B2, A3, B3. And now you see here, first this full adder 1 will operate and will generate a carry, right? And once this carry is generated, then only this full adder 2 will operate and will produce carry 2. Now once this carry 2 will be generated, then only this full adder 3 can operate, right? Before this it cannot operate because then it will be wrong. Then C3 will be generated, and once this C3 will be generated, then only this full adder 4 can work, and finally our C of C4 can be produced. Respectively, sum will also be there, that is sum 0, sum 1, sum 2, and sum 3. Right? Now, in order to produce this C out, you can see that C out is dependent on C3, C3 is again dependent on C2, and C2 is again dependent on C1. Right? So how many processing stages are there? 1, 2, 3. 3 processing stages are there. So it will have some propagation delay. Now, in order to reduce this delay, we have implemented look ahead carry adder. And we have implemented this by looking at the truth table of the full adder, and we have come to the conclusion that if you implement this logic, then that final carry out should not be dependent upon the previous, but it has to only depend upon the input carry in. So by putting the equation, and if suppose this is a 4-bit number, so this fourth carry out, you can see right now it's not dependent on C3, but it is only dependent on C0. You can see here, right? Now you can implement this logic by SOP because this is in sum of product form. So you can implement it by using NAND gate. So that is why I have double complemented it, and then I have applied the De Morgan's here. Right? This step is De Morgan's here, and so this you can implement it. G4 does not require any gate, so I have kept it same. If you see P3 into G3 bar, how can you get this by NAND gate? You have to provide P3 G3 and one NAND gate. So this input you can see here. Similarly, this if you have to take out this, so here 3 input NAND gates will be needed. Are you getting this point?
Yeah, yes, sir. Yes, sir.
Okay, so 3 input NAND gate will be needed, and finally one bar has to, and finally the multiplication of this has to be also be done through NAND gate. So you can see I have implemented one more NAND gate, and if you implement this NAND gate, so input of this NAND gate will be the previous input of other output of other NAND gate, and so finally C4 we will be getting. Now once you have implemented this carry look ahead, this is look ahead carry. This is look ahead carry logic. Once you have implemented it, then you can see here how much is the processing time, right? How much is the processing time? So first, this is 2-level conversion. This is first NAND gate. All the NAND gates will be switched at a time, and then this is second NAND gate, right? First, this NAND gates will be switched, and then this NAND gates will be used. So this is a 2-level logic, right? So only how much processing time is needed here? 2-level processing time. So you can see if we are having a 64-bit number, and if you have to add, so in that case a 64 processing delay will be there in order to get C out, final C out. But if you are using this NAND logic, so only 2-level delay will be there. So you can compare how much is the time we have saved, right? From 64 propagation delay, that is 64 times, and it is only using 2 times. So if something is needing 64 microsecond, let us say, so if you apply this carry look ahead logic, that will only require 2 microseconds. So we have reduced a time. But what is the disadvantage? Disadvantage is that you have to implement extra hardware. And what is the disadvantage of extra hardware? Extra complexity will be there, and more important,
memory space will be used.
More expensive. Correctly, it will be more expensive. So ultimately, if you want to take the advantages, like if you want to operate in a fast system, so it has to be more expensive. You can follow this trend in today's scenario as well. So which is the mobile phone which are having more processing time or which is very fast are little bit more costly, right? So this is the same thing. If you want to improve something in your system, some drawbacks will always be there. So this is a simple logic of carry look ahead adder. So we have explained it. I have explained it using 4-bit. So now you can implement this.
Sir?
Yes.
So now if the number of bits are increased, so the delay will be more or less?
Number of bits are increased, and if you are using carry look ahead error, then
for example, now we have used a 4-bit. If I
yes,
increase it to 12 or 16, so will the delay be more or less?
In which case? Parallel adder case or this carry look ahead? Parallel, yes, obviously delay will be more. Delay will be more. No? For 12-bit, for 16-bit number, 16 full adder have to be implemented. Correct?
Yes, sir.
And carry out of each stage has to be propagate.
Yes.
So let us say this is 16 C16 or C out, and this is our carry in, which was 0. So each stage carry has to be generated, and for generating carry, we have seen that this is full adder 1, and we have also seen what is the circuit of full adder 1 using NAND gate or NOR gate, right? Big circuits are there. So each and both NAND gate and NOR gate, how many levels were there? So that is also 2 level. If we are having a NAND gate, so that will also have 2 levels of processing. In first level, all the NAND gate will be there, and in second level, output of first level will go to the second NAND gate, right? So 2-level processing will be there. And,
Yes, sir.
and so this carry 1 will be generated. See, similarly for this full adder 2, again the same thing will be there. Similarly till 16th bit, so all these circuits will be there in series, and carry will ripple through this carry 1, carry 2, carry 3, and ultimately your carry 16 will be generated. So propagation delay has to be there.
Yes, sir. Time complexity increases. So.
Yes, but if you implement carry look ahead adder, so there we have seen that this C16 you can easily get by implementing some extra hardware, and this is only dependent on the input carry, right? So this extra hardware you can implement it through NAND logic, because it was in SOP form that we have seen, and this SOP form or NAND logic will only require 2 level of propagation delay. Okay.
Yes, sir. Yes.
Okay. So now, if you want, you can show this in block diagram form as well. So let us say this is P4 and G4. Let me use some other pen. So P4 is what? That is P is what? A XOR B. We know this. And G is what? A multiplied by B, right? So I can use two things, that is A and B here. And in P there is XOR operation. So this is XOR operation. And in B there is AND operation. Right? So this is P4 and G4. Similarly P3 and G3, P2 and G2, P1 and G1. So same thing will be there. This is, let us say this is A4 and B4. So this is A3 and B3. XOR will be gate will be there, and AND gate will be there. XOR gate will be there, and AND gate will be there. XOR gate will be there, and AND gate will be there. So B3 is flowing in this way, and this is flowing here. Here A2 and B2 will be there. This is flowing here. This is also flowing here. Similarly, A1 and B1 is there. A1 is flowing here. B1 is also flowing here, and this is flowing through the AND gate. Right? This is our this, and finally we can have C in as well, or C in, that is Cn minus 1. So this you can call it as C1 or C in, and then we will have here carry out, that is fifth, or you can call it C5 or C out, you can also call it. This can be generated, and you will also get C4, C3, C2. So sum will be P4 XOR with this, so this will be sum 4. So this is just a block diagram way that I am drawing. This is P3, this is sum 3, and this is flowing again to XOR. So this is sum 2, and this is P2, and this C in is again going to the XOR gate, and this is P1. This is sum 1. So this is a 4-bit carry look ahead adder in a block diagram way. But once this expression is obtained, so you can easily draw by your own logic. Which expression? This expression. This expression is must. Okay. So you have to understand how this expression is working. This is about the carry look ahead adder. Now we will see other logic, that is BCD adder. Just wait for a few seconds. Am I audible?
Yes, sir.
Okay, now we will see BCD adder. So that is binary coded decimal. So suppose if you want, let me just give you a review. What is BCD adder?
Sir, can you scroll up to the block diagram once?
Just wait. Yes.
Yes, sir. Yes, sir. Okay.
Okay.
Yes, sir.
So BCD adder. Suppose if you want to add two numbers in BCD, so I will just give you a review what it is. Suppose if you want to add 35 and 49. So if you sum this, so this will be equal to 4 and 8. 84 is the number that we will be getting. Suppose if you want to add similar number in BCD, so one decimal bit will represent 4 bit in BCD. So 5 can be written as 0 1 0 1. This is 5, and 3 can be written as 0 0 1 1. Right? Similarly, 9 can be written as 1 0 0 1, and 4 can be written as 0 1 0 0. Now you have to add this in BCD. So this will be 1 plus 1 be 0. 1 will be 1 here, 1 will be 1 here, 1 will be here, and similarly 1 will be here, 1 will be here, 1 will be here, and 0 will be here, right? So you can see that this is not a legal BCD, because maximum a 4-bit BCD can have 1001, which is equivalent to 9, right? If you want to represent 10 in BCD, how you can represent? So 1 you can represent by 0001, and 0 can be. So this is how 10 can be represented, right? So maximum legal bits are 1001. Right now you can see that it is not the right form of BCD. So what we have done here, we have added a 6 here. So this will be 0110, and this is legal because this is right now 7. So if you add this, so this will be 0 0, 1 will be 1 here, 1 plus 1 will be 0, and 1 plus 1 will be 1 1. So 1 1 1 will be 1 here, 1 0, and 1 will be gone above. 1 plus 1 will be 1 0 1 0 1 0 and 1. So now you can see this is our right answer, where 100 will represent 8 and this will represent 84, right? So this logic we have to implement it in our using our logic gates. This much is clear. This concept is clear. This we have already seen.
Yes, sir. Yes, sir.
Okay. So so add the 4-bit BCD code for each decimal digit position using ordinary binary addition. So this we have seen. Using ordinary binary equation we have added, right? In this case, if the sum is less than 9, then no correction is needed. If the sum is less than 9, then no correction is needed. That means it is in true BCD form. It is in true BCD form. For example, if you want to see that true BCD form, let us say 23 and 11, and so addition of this will give you 4 and 34. So 3 in BCD can be written as 0 1 0 0 1 1, and 2 can be written as 0 0 1 0, and 1 can be written as 0 0 1 1. Sorry, 0 0 0 1 0 0 0 1. You can add this, so this will be 0 0 1 0 1 1 0 0. So right now you can see that this is not greater than 9. This is 4, and this is also not greater than 9. This is 3. So this is in true binary form. Hence no correction is needed, right? So this is first case. When the number is greater than 9, which we have seen in our previous case, which was in this case, right? When the number is greater than 9, then correction is needed. And what is that correction? We have to add 0 1 1 0 to it, whichever is our illegal bit should be added, and this will produce a carry. This can produce, by addition of this can produce a carry which will be gone to next number, right? We have seen. So steps to draw the BCD adder. Steps to design BCD adder. So first is add two 4-bit BCD code groups. Second step is determine if sum is greater than 1001, that is 9. If sum is greater than 1001, that is 9. If it is greater than 1009, then add 0110, that is 6, to this sum and generated carry to next decimal position. For example, let us take two binary number. Generalized term now I will be doing, that is A3, A2, A1 and A0, B3, B2, B1 and B0. This is our first binary BCD number, and this is our second BCD number. And suppose we want to add this BCD addition, right? So it will be producing sum 1, sum 2, sum 3. And suppose if carry is also generated by addition of A3 and B3, carry is also generated. So let us just call it sum 4. So sum 4 here is denoting what? A carry. Right? Now we have to check this sum 4. This sum 4 has to be less than 1010, that is 10. Right? So this has to be less than 1010. So if you see this sum range, this is sum range, right? This is 5-bit number. So what is the sum range? The sum range can be 0 0 0 0 0 to 1 0 1 0, right? This can be the range of sum. Why this can be the range? This will be the number when both A and B, both the BCD number are 0. If both are 0, we will be producing 0, right? And maximum BCD number can be 9. If both the numbers are 9, are 9, then what will be produced? Just see. Both the numbers are 9, that is 1001, 1001. So this will be 0, 1, 0, 0, 1. So you can see if both the numbers are 9, because why 9? Because this is the maximum number which BCD can represent. So we are taking the maximum possibility. So if both the numbers can be 9, so this number can be produced. So our sum will be ranging from, sum means this 5-digit number can be ranging from 0000 to 1001. This is clear? What is the range?
Yes, so 9 is inclusive or exclusive?
9 is inclusive, because 9 can be expressed in BCD, because in 9, how can you represent? This is BCD of 9. But for 10, how you can represent 10 in BCD? That is 0001 and 0000. Right? So this is the 10 representation using BCD, and this is 9 representation. So each decimal bit will, each decimal place will need 4 bit of 4 places in BCD. This range is clear?
Sir, can you explain again?
Which thing should I
The
explain?
range.
Okay.
The range.
So suppose if you are having two BCD number, that is A3, A2, A1 and A0. This is the first BCD number. Second number is B3, B2, B1 and B0. Right now what we are trying to do, we are trying to design a BCD adder. Correct? So these 4-bit 4-bit BCD adder, right? So if you add this, so this can produce sum of sum 0, sum 1, sum 2, sum 3, and carry will also be generated. So let us just call it as a S4. So how many bits are there? 5-bit, right? So in this 5-bit, now we have to classify between what are the legal bit, what is the legal bit, and what is the illegal bit, right? So what is the legal bit? If you see zeros, so what will be the range? Range can be 0000 to what will be the maximum range? What can be the maximum number of this? What can be the maximum BCD number? 9. So how can 9 can be represented? 1 0
1 double
0
0
1. What will be the maximum number of this? Again 9. It can also be represented 1 0 0 1. So if you add both these BCD numbers, so this will be 0 1 0 0 1. So what is the maximum number of this range? That is 1 0 0 1 0. So this is the range of BCD addition. Now is it okay? Range is okay?
Yes, sir. Yes.
Okay. So now if you see, now we have to identify which are the legal bits and which are the illegal bits. How you can identify? So if you are representing, if the carry is not generated, suppose so from 0 0 0 0 to 0 1 0 0 1, these are all our legal bits. So what is the rules of BCD? If carry is generated, then also you need to correct that bit. If the number is greater than 9, then also you need to correct that bit. So these are our legal bits. So we will not focus on our legal bit. We will just focus on our illegal bit. So let us just say, because this will represent what? This will represent 9, right? So let us just say we are having 5 digit. That is S3, S4, S3, S2, S1, and S0. And the first illegal bit can be 0 1 0 1 0. This is what this is representing in decimal. This is representing 10. Similarly, next illegal bit can be
0 1 0
0 1 0 1 1. Next will be 0 1 1 0 0 0 1 1 0 1. Just pay attention. 0 1 1 1 0 0 1 1 1 1. Next can be 1 0 0 0 0 and 1 0 0 0 1. Next can be 1 0 0 1 0. Now we will stop because this is our maximum range, right? So we have reached this range. There is no way you can produce a sum of BCD number greater than this number, right? 4, which is having 4 bit. So this is our maximum bit. So this is our all illegal bit. So this represent 11, this represent 12, this represent 13, 14, so on, 15, 16, 17, and 18. So 9 plus 9, if you see, it is 18, which is coming here, right? This is the maximum limit of BCD addition. Now we have to develop a certain logic that will tell us that our sum bit is illegal. So let us say that logic is X. So this X will always be 1 if our bit is illegal. This X will always be 1 if our bit is illegal, right? So we have to define this X with the help of our logics, right? So X, you can say that X is a variable. X is a variable that will be high, or you can call it 1 whenever sum is greater than 0 1 0 0 1, which is 9. So we have to define X. Up to this point, is it clear? We have to define X. Up to this point, is it clear?
Yes, sir.
So just see whenever, so we have to develop a logic. So can I say one logic that whenever our S3 is on, or whenever our S3 is high, whenever our S4 is high, this is an illegal bit. So S4 is high is our one logic. So S4, this is our S4. Whenever S4 is there, whenever S4 is present, so that can be one logic. And the second logic you can see you have to develop a logic between these numbers, right? What can be second logic? So the second logic that you are seeing is S3 is always high. You can see S3 is always high, and if you observe these two, S2 and S1, if you take the sum of it, then our logic will always be high. If you take sum, that is S. If you take the logic like this, that is X is equal to S4 plus S3, S2 plus S1, right? If this is high, then our logic, then our bit, that is X variable, that is X, will always be high. In all other cases, this X will give 0 value. Just check if our bit is high. If our bit is illegal, then our X will always be high. How? Let us just check. Let us just check for this first number, right? See, what is S4? S4 is 0. What is S3? S3 is 1. S2 is what? S2 is 0. XOR with S1. Sorry, or with S1. S1 is 1. So this will always produce 1. So 1 into 1 will be 1. So 0 plus 1, this will be 1. So X is 1, high. You can see here. So this logic is there, which you will use if you will use. Similarly, there can be many more logic, right? But if you use this logic, you will always get X is equal to 1. One more case you can consider. So let us just check for one more condition, that is X is equal to S4 plus S3, S2 into S1, right? Let us just check for this 18th number. So at the 18th number, you can directly see that S4 is 1. S4 is 1 plus S3 is 0. 0 multiplied by anything will be 0. So X1 is 1, right? Now, if you want to check this logic for lower bit, that is for legal bit, let us just check that as well. So X was given by S4 plus S3, S2 plus S1. Let us just take a legal bit, that is 0, 1, 0, 0, 0. This is representing 8, right? So let us just check for this case. S4 is 0, S3 is 1. So this is your S4, S3, S2, S1 and S0. S3 is 1, S2 is 0, S2, this is also 0. So this XOR 0, XOR 0 or with 0 will give you 0. So this logic will be 0. Again, if you check for one more legal bit, that is 0. Let us say 0, 0, 1, 1. This is 3. This is also a legal bit. So in 5 bit, this can be this. So this is S4, S3, S2, S1 and S0. What was our logic? X is equal to S4 plus S3, S2 plus S1. So S4 here is 0, S3 here is 0. So 0 multiplied by anything will be 0. So you can see that whenever our bit is legal, X is 0. Whenever our bit is illegal, our X is high. So we have developed a logic by looking at this truth table. Just tell me whether this is clear, or should I explain it again? Am I audible?
Yes, sir.
Okay. So our X logic was coming as S4 plus S3, S2 and S1. Now we have to implement this logic, right? So just pay attention. We are having 4-bit parallel adder. And the name of the IC I have told you, that is 74LS83. There can be many more ICs, right? So in one end, there is one input, there is another input in this end. So let us say that this is input is B0, B1, B2 and B3, and this input is A0, A1, A2 and A3, right? And our carry out, you can say that this can be carried in from previous stages. This can be carried in from previous stages, and this will produce an output of sum that is S0, S1, S2, and S3, and one carry out will also be produced, which we called it as S4. This much is clear, right? So now we have to implement this logic. So just see S4. I will implement this logic. So this is S4 I'm taking, and it is OR with S2 and S1. S2 and S1. This is S2, and this is S1, and this is XOR. Sorry, this is OR only. This will be S2 plus S1, and this is multiplied by S3. S3 is this. I will have to pass it through AND gate. So this logic is S3 into S2 plus S1, and finally I have to add it with S4. So just see, I have to add it with S4. So this will be again passed through an OR gate. So this is our X, right? So this is our X, and this X will again flow. This is an error corrector, or if any correction is required. When correction will be required? When our bit is illegal. Now we have to use one more 4-bit parallel adder. Just pay attention. So this is 4-bit parallel adder again, where the input now this time will be the previous sum. Previous sum was S0. S0 will be flowing here. S1 will be also flowing here. S2 will be flowing here, and S3 will be flowing here, right? So this is our I have put S0. So this second 4-bit parallel adder is acting as a corrector unit. If the bit is illegal, then we need our correction. And what is the correction we needed? We need to add 0110, that is 6 to it, right? So you can see that least significant bit is 0 and most significant bit is 0. So if there is 4 input here, I can put least significant bit to the ground and most significant bit to the ground. Ground means this is a symbol for ground, that is G ground, or you can also call it as GROUND ground. This means low level, that is 0, right? And remaining this will be high. Whenever it will be high, when X will be equal to 1. So just see, this X is flowing here. So this, whenever X is 1, so X is 1 means the bit is illegal. So you need to again perform the sum operation. So this is, you can say this is sum 0, sum 1, sum 2, and sum 3. So whenever our bit is illegal, this X will be always 1. And when this X will always be 1, so you can see that we are again adding to the, whatever our sum was, we are again adding 0110 to this sum. And we are again producing the output bit. That is D0, D1, D2, and D3. And this will be C out, or you can call it as a D4, right? And when the bit is legal bit, then you know that if the bit is legal, then X will be equal to 0. And if in that case X will be equal to 0, then this logic will become 0, 0, 0, 0, and nothing correction will be needed, and you will get D3, D4, D3, D2, D1, D0, same as S3, S2, S1, S0. This logic is clear?
Yes, sir.
Okay, so one more logic will be there. So this will be C naught. C input in this case will be also be 0. So again, I have shown it by ground. You can show it. You can directly show it by ground, or you can also write C in is equal to 0. Whatever you prefer, you can write. But main thing is that you will be needing two 4-bit parallel adder. In first bit parallel adder, you have performed the sum. Just see, and you are generating X. Why you are generating X? To differentiate between legal bit and illegal bit. So this, if X will be always be 1 if the bit is illegal, and for illegal bit we have developed a logic, which is this logic. And so this logic, you can see I have drawn it here in this case, right? And this will always be 1. If our bit is illegal, then we need to add 0110, that is we need to add. So we need another 4-bit parallel adder, which is shown here. So output of this, that is first 4-bit parallel adder, is flowing to this, and if any correction is needed, so this 0110 is again flowing. So this will be 1 if the bit is illegal. So this again, there will be addition, and we will be producing this D3, D2, D1, D0, and this D4 again. If the bit is not illegal, if the bit is legal, then obviously this X will be 0, and 0 will be again added. So you will be getting same sum as same D3, D2, D1, D0 as S3, S2, S1, S0. Is it okay?
Sir, please take the attendance, sir. We have
Sorry?
next class. Sir, please take the attendance, sir. We have
Yes,
next
yes,
class.
yes, yes, yes. So I hope this BCD adder is clear.
Yes, sir.